did you join Stanford?
Just a few months ago.
People at Stanford or you?
This is with people, one person from Chicago, one person from Notre Dame, and one person from University of New Mexico.
Oh.
Yeah, I get around.
Okay. Let's wait 2 more minutes.
Okay.
To make sure that that's in the 2 minutes.
Like the cameras so that they would do the abstract
Smart.
everybody and yeah.
Is that okay?
Yeah, I think yeah, that's great. Thank you.
Just start. Okay, so hello everyone. Today we're very happy to have Aurora Ireland from Stanford. She got her PhD in Chicago, under supervision of Marcela Carena, right?
Mhm.
And then she is currently doing her first postdoc in Stanford University. And today she's going to talk about the CMB B-mode from Cosmological Phase Transitions.
Cool. Thank you. And thank you for the invitation. Happy to talk about this really fun project that I did with Gordon Krendijk, who's at UChicago, Yushin Tsai from Notre Dame, and Kyler Green, who is a student at the University of New Mexico, currently on the postdoc market now, and really, really great with numerics. So this is on CMB B-modes from Cosmological Phase Transitions. Right, and I want to start with a quote, and I just pulled it from like a random paper, but you'll see something along these lines in many papers. So tensor fluctuations are a prime target for future observations of the CMB because if detected, they can provide a conclusive verification of the theory of inflation. Or slightly more punchy, detecting a B-mode polarization in the CMB is a smoking gun for an inflation. With the little asterisk being above astrophysical foregrounds, because we do expect some degree of B-mode polarization pattern from things like gravitational lensing and whatnot. Right, I don't know that I really need to motivate inflation too much. It solves the horizon and flatness problems, and it also gives an origin story for the perturbations that seeded the large-scale structure we see today. So inflationary models pretty generically predict scale invariant spectrum of tensor perturbations. And these induce this very characteristic B-mode polarization pattern in the CMB, which we haven't seen yet, but if we did see it, it's pretty universally agreed that this would be finally smoking gun evidence of inflation. I did mention that there are a few other things that do give rise to B-mode patterns that we know about. There's gravitational lensing, which can convert an E-mode pattern to a B-mode pattern. And then you can also just have like dust and foreground noise that does some unavoidable degree of lensing. But really, inflation so far is, I know, when we embarked on this project, was the only direct primordial source. And the pattern, so this is the angular spectrum of B-mode polarization. On the x-axis here is multipole moments. So small l corresponds to large scales, large L corresponds to small scales. And then the y-axis, of course, is the angular spectrum. And then in blue, we have what the polarization pattern looks like from the inflationary prediction. Here for a tensor to scalar ratio of 0.03. And here for 10 to the minus 3. So it has this very characteristic shape. It has the recombination peak around 100 or so, and then larger scales, it has the reionization peak. So that's kind of what we expect from inflation. The exact amplitude depends on what R is and if it, deviates from scale invariance. But then in green here, we have what the lensing signal looks like. And then here we have some data.
And so how do you even tell the difference? Because we've already been down this path, right, with bicep originally declaring evidence for inflation.
Yeah.
So what's the, we have to know back. Yeah, so how do we know that?
That's probably a better, I feel like an experimentalist could probably answer that question better than I can. I just accept that we can de-lens the signal, but to be transparent, I don't know exactly.
Dust, since you know how much dust there is, then you can figure out what its effect on the polarization would be. And there are all sorts of effects that you know about. I mean, that's the problem with what happened with bicep is that they didn't do it correctly. And so I was just wondering what the improvement was from bicep because they didn't do it correctly at the time.
Yeah, but later on, they use the class data to do the overall subtraction properly.
So
They use the class data to do the overall subtraction properly and then undiscover there.
right, instead of
Bicep process is this, right? So bicep has a newer lens. You may rely on other data.
but right now, all they're doing is setting limits on R. Because you see, if you, there it's written as 0.03, if you put it at 0.05 or 0.06, for example, it would be above where they're starting to see points, and so they get an upper limit. I mean, in principle, you'd like to see it at large. You have to get, the smaller the amplitude, the larger scale you have to look at it, because you're going to be swamped by it there.
Yeah, and basically no one thought that the dust in the Milky Way was ever going to, so they didn't figure that stuff out. So that's what they're hoping to thought it would. Yeah.
Right. Thank you very much. Okay, so apparently we know how to de-lens a lot better than back in the bicep days. Right, but again, I'm going to be talking about a new theory prediction that hopefully will make things even more complicated. Okay, so in principle, any source of large-scale coherent tensor perturbations that are produced before reionization, though, could contribute to B-mode polarization. And the example that I'm going to have in mind is first-order cosmological phase transitions. So these produce tensor perturbations / gravitational waves. I'm going to use those words interchangeably in 3 distinct stages. So first order phase transitions occur through the nucleation of true vacuum bubbles in the metastable phase, and you can get gravitational waves when these bubbles collide. Even after the bubbles collide, fluid kinetic energy propagates through the plasma, and you get collisions of these acoustic waves, and that also sources gravitational waves. And then that also creates turbulence, which has its own contribution. So cosmological phase transitions, if they're first order, come with a lot of ways to produce tensor perturbations. So typically the peak power is on small scales, though, because these are happening in the early universe. Things that happened in the early universe are associated with smaller scales. But on large scales, they do have support in the power function and the power spectrum. And in particular, the IR tail of the power spectrum is going to have this K⁻³ white noise spectrum that's characteristic of causally limited modes. So generically, you would expect this contribution to be negligible. I expected this contribution to be negligible. Actually, the way that this project started was Gordon was proposing that you could have something like this, and I was kind of skeptical, so I did the calculation to try and prove him wrong, and then found that actually it looks like maybe you could have something. So why do I say that you expect it to be negligible? Well, essentially just because the CMB is sensitive to long wavelength stuff. So modes with co-moving wave number around or less than like 10 to the minus 2 inverse megaparsecs, that's not precise. You know, it has support on slightly larger scale, slightly smaller scales too, but that's like where it has its most support. And because of this fall off of the IR tail, you wouldn't really expect the phase transition power spectrum to have much amplitude on these scales. You would expect it to be suppressed. So essentially, because phase transitions are something we think of as like early universe, small scale things, and the CMB is like late, relative, and large scale, you wouldn't really expect it to have much overlap. But my claim is going to be that for certain phase transition parameters, actually, this is not the case. You can have a signal.
Why that should happen before reionization to
Just because so I'm gonna get into this when I talk about how the B-mode polarization is baked in. Actually, can I just defer that to a
Sure,
few
yeah.
slides? Okay. It has to do with the visibility function.
So these modes that you're going to be looking at the time that they're produced, they're far outside the horizon.
Yeah, these are superhorizon modes
Okay.
initially.
And like causality doesn't, that like you somehow get around causality issues.
No, that's why it's a white noise power spectrum on these superhorizon scales, because it's so these are modes that have wavelengths that are much larger than like the causal correlations of the source, which is why you expect the power on these scales to just be random. White noise is just random power spectrum.
Okay, but causality doesn't prevent you from having something. It just means it has to be white noise.
Yeah.
Okay.
Yeah.
Okay.
Yeah, right. Okay, so the two main claims that I want to argue here are that the tensor perturbations from a strongly first order phase transition can produce a B-mode signal whose strength can match that of inflationary predictions across a range of potentially observable scales. And that's bad if you're a fan of inflation, but the scenarios can be differentiated if you can perform measurements on multiple scales because the spectral shapes are going to be distinct. In particular, as you might expect, the phase transition is going to have more power on smaller scales. So unfortunately, this area where the lensing signal is very strong, but presuming we can de-lens things properly, we could differentiate these scenarios. Okay. So that is kind of the motivation. Now I want to review how B-mode polarization gets baked in. I'll review how to calculate the tensor power spectrum from a phase transition, and then I'll get into our results. Okay. So very generically, scalar and tensor perturbations in the early universe results in temperature anisotropies. And these temperature anisotropies get transformed into polarization when you have Thomson scattering of photons with free electrons. So some photon comes in, jiggles the electron, and then light comes out. And because the light can't be polarized in the direction of motion, this sort of thing will give you only one linear polarization.
Or you need the quadrupolar.
Yeah, you're 2 slides ahead. Yeah, so if you try and do this with dipole, it's not going to work. Because yeah, well, if you try and do it with a dipole, because these guys, if they have equal intensity, you're going to produce both linear polarizations in the same amount. So that's not going to give any net polarization. What you need is the quadrupole. Quadrupole anisotropy in the temperature distribution, and now you can have a net linear polarization. So right, these are the different classes of quadrupole anisotropies. You've got the scalar mode, the vector, and the tensor. Scalar is going to come about from density perturbations. Vorticity will produce the vector pattern, but that's kind of negligible by recombination, so forget about that one. And then the only thing that'll give you the tensor pattern is gravitational waves, really, or tensor perturbations. So then if you project these quadruple line isotropies, that's what's going to give you the polarization pattern. And it's convenient to decompose this into two parts. So you can decompose it into a divergence piece. This is the E-mode polarization in analogy with the electric field, which has a divergence. And this pattern is unchanged under reflection. It's parity even. And both scalar and tensor perturbations will give you this pattern. The B-mode polarization pattern is the curl piece. This one is parity odd. They transform into one another if I do a reflection. And this one, only the tensor perturbations will source this pattern directly. Okay, that's at a glance how this works. Let's make this quantitative. So I want to derive an expression for the angular spectrum of B-mode polarization. To make my life easier, I can make an I'll relax it. Obviously, we relaxed it for the actual calculations, but just to get some formulas on the board, we can assume that most of the polarization, or essentially all of it, is going to be generated at last scattering. Why? So at recombination, the number density of free electrons is going to drop sharply. And because of that, Thomson scattering is going to cease to be efficient. You do get the visibility function has like another peak around reionization, and then it drops again, which is why reionization is when I said you need it by. Right, so I'm gonna go ahead and assume, for the sake of getting some formulas on the board, that we're gonna generate our polarization at last scattering.
And you're neglecting anything before last scattering.
Yeah.
It's okay.
Yeah, because it's just gonna average itself out. Yeah. Yeah, so I'm gonna just assume that there's some small window of time around recombination where things are gonna get polarized. And if you want, you can look at the paper for some gory details, but this is kind of just, this is well known in the literature, and I don't want to just have a bunch of formulas, so I'm just gonna schematically show how you calculate the rough expression. So you have a tensor perturbation from some source, be it a phase transition or inflation or whatnot. This gives you a temperature anisotropy. The temperature anisotropy enters into the polarization temperature, the polarization tensor, which you can decompose into E and B mode parts, and you expand them in spherical harmonics on the celestial sphere, and then you can isolate these coefficients. And then from those coefficients, you can define the CLBB thing, which I was plotting on the y-axis on the plot a few slides back. So this is just the 2-point correlator of these guys, then integrated over momentum. So if you actually do this for in all its gory detail, this is what you get for CLBB. So it's an integral over the power spectrum. So the dimensionless tensor power spectrum, that's going to be this curly P with the subscript H. And then this horrible F thing. I put these formulas up because, I don't know, there might be some experts in the audience that this is useful to see. But if you're not, honestly, I just think about this thing as kind of a window function that's picking out the modes that the CMB cares about. If you look at its structure, it's got the visibility function. Actually, I think I labeled these on the next slide. I did. It's got the visibility function. It's got this function of spherical Bessel functions, another visibility function, another spherical Bessel, and then the transfer function. The important thing is it's just like a window function that. Are there any markers?
Some on the opposite desk here.
Yeah.
Thank you. Okay, that's okay. There's a plot in a few slides. It's It's fine. Sorry. It's,
Or maybe you can explain the structure of this window function. The
In case you want one in the future.
yeah.
What are these three integrals in class?
Well, the visibility function is gonna have like it's gonna drop off sharply after, so tau here is conformal time. So it's,
So why do I split into three pieces and why visibility function appear twice?
it's a good question, and I would have to review the derivation.
Okay.
Yeah, I don't have a quick explanation, but I can show you afterwards if that's okay. The thing I just want to point out, and it depends which L function you're looking at, but very generically, this is going to be my K. Very generically, this thing is going to have kind of like a broad peak here. It's going to fall off like this as you go to larger scales. And then it's going to fall off very sharply as you go to smaller scales and really oscillatory. I think there might be oscillations on the side too. The important thing though is just it has support on larger scales for the most part. Okay, I regret showing this. Okay, so the thing that we need in order to evaluate this formula, because this is something that's just known, I need my power spectrum for the tensor perturbation. And that can either be from inflation or here I'll do it for a phase transition, but that's the specific ingredient I need. So to compute this power spectrum, I need this 2-point correlator of these the tensor perturbation evaluated at some initial time. I'm going to go ahead and decompose my tensor perturbation into some initial amplitude, and then all the time dependence I'm going to absorb into a transfer function. This is just nice because it'll separate the effect of like the actual statistical correlations of the particular particle physics model or whatnot from the deterministic evolution. The transfer function is gonna obey the sourceless wave equation. There's a little bit of anisotropic stress here from neutrinos, but ignore that. For the most part, just treat it as free. And the explicit forms aren't too important. The important thing about the transfer function is just when you're outside the horizon, it's flat. It's like frozen in. And then when you enter the horizon, it's gonna fall off and start oscillating really sharply.
The PH you had on the previous slide, that's the power spectrum of the initial perturbation, the initial tensor modes, or the power spectrum of the final?
That's a good question. I'm guessing it's the initial because we have the transfer function entering here. Yeah, it's the initial. Yeah.
Okay, the transfer function gets baked into this window.
Yeah. So I think there might be a bit of a notational inconsistency here.
Well, that's.
Oh, no, because we define it that way. Yeah. No, thank you. Okay, yeah. So this is already taking into account that we've baked the transfer function into our definition of the window function. And we're just defining the power spectrum at some initial time. Okay, so the next step is let's compute what the tensor power spectrum is. So again, I'm considering a first order cosmological phase transition. So these proceed via the nucleation of these bubbles of true vacuum in the metastable phase. And as these guys expand, they're gonna collide. In this first phase of sourcing gravitational waves, they're gonna collide. This is gonna break spherical symmetry, and then the gradient energy of the scalar field itself is gonna source the anisotropic stress. Next, even after that completes, you're still gonna have like fluid kinetic energy that's propagating through. And when that collides, that can also source these tensor perturbations. And then if there's any energy left over, these sound wave collisions can give you turbulence, vorticity, instabilities in the fluid. And this also contributes to some degree. This is the most uncertain source, because you really need to model these things numerically, and not sure what the status of that is. I'm gonna focus on this first one because it's something that's really well understood. I'm gonna pick a type of phase transition where the dominant contribution is coming from the first one, because the bubble collision stage is something that's fairly well understood. And actually these two authors, Gino and Takamoto, actually went through and calculated what the 2-point function of the stress tensor looks like in that case. So we're gonna focus on that one. So in that motivation, I'm going to consider a strongly supercooled first order phase transition. Supercooled, by that I just mean that the temperature where the transition completes and the initial like critical temperature, there's a large gap between those two. And strongly supercooled phase transitions are nice because the plasma friction, which normally acts to slow down the wall, the plasma gets diluted. So you really don't have as much friction as you otherwise would, and you typically have these runaway bubble walls. And usually the dominant contribution to the tensor perturbations is going to come from the sound wave phase in most phase transitions, but in these types, it'll come from the bubble collision phase. So I'm just going to focus on that source. So, right. The first thing I need to know what H is. I know what H obeys as far as equations go. It's this sourced wave equation. This source here is the Fourier transform of the transverse traceless stress tensor. So you can think of it as just Tij, but the transverse traceless part, and then Fourier transform that. It's statistically homogeneous. It's isotropic random variable. And the other thing is it's short-lived, quote unquote. The phase transition completes fast in a sense in that it completes in a fraction of a Hubble time. But as far as phase transitions go, these guys are going to be the longest lasting ones. So that's why fast is in quotes.
Well, so just one question. High energy here, I guess that's the energy with the tensor scalar field.
Yeah, of the scalar. Yeah. In general, it's whatever is sourcing your tensor perturbation. So here it's the scalar field from the bubble collision phase. Yeah, and I guess another thing I should say, just because this was something that I was initially didn't understand, is that when the bubbles collide, the point of the collisions themselves is just to break spherical symmetry. It's the scalar field that's actually sourcing that's the thing in the stress, like the gradient energy of the scalar field or whatever is the thing that's sourcing your anisotropies.
Being strongly first ordered, you don't enter another inflationary phase.
I mean that is a possibility, but if you choose your parameters right, no. Yeah, I mean that is a possibility, and you can also have weird things happening, like I don't know, you can also form primordial black holes or baby universes, or you can have another eternal inflation phase. But this project is kind of like a proof of principle. We're not exploring this in the context of a realistic particle model. And I think that would be a really useful exercise to do after this. This is this is just assuming that I have my phase transition and it has it's just perfectly calibrated to give me a beta over H star of 2 and a alpha of whatever. Like the thermal phase transition parameters are what they are, but it would be good to derive those from like a underlying particle physics model. In that case, you could check that you don't have any of these I guess, undesirable scenarios.
But what happens to the scalar perturbation?
You have constraints on those because it's unavoidable that that's gonna constrain our parameter space.
And the small enough height of the Paul spectrum of this scalar theory.
Hmm?
Because you're assuming the first order phase transition. The scalar is sitting on first spectrum for a long time.
Yeah.
Furthermore, you're requiring the late-time phase transition. So the question is that in order to have a significant B-mode polarization contribution from this phase transition, can you have a small enough height of the first spectrum of this scalar field potential, which can be small enough to not to spoil the radiation illumination and matter illumination. And even in that case, even for the small height of the pulse vector, can you still have a significant contribution to B-mode polarization? I think that's one.
Yeah, that's another way of asking that. My gut feeling is yes, but it's something that I would want to check more quantitatively. I do know that, I mean, typically if you want strong supercooling like this, you want something that's classically conformal invariant. So that's kind of the type of potential you're gonna have, like something that's very flat at tree level. I need to check.
At least, but you should have two different vectors.
Yeah, no, but they're radiatively generated is what I'm saying.
Whereas like this height of the pulse vector should be as small as, for example, dark energy, which does not affect the cosmology of radiation emission era.
Yeah, I think because the barrier or whatever, the second vacuum is radiatively generated, it can be small. But it's right. Okay, right. So we were calculating H. So because this so first I want H during the phase transition itself. So during the phase transition, because it completes kind of fast within a Hubble time, I'm gonna make my life easier by neglecting expansion. You can include it, it doesn't really change things. And in this case, I can just solve this by the method of Green's functions, and this is the expression I get for H. After the phase transition, I should really take into account expansion. Why I'm actually solving after the phase transition will be apparent later, because you would think that, you know, if you have it during and you evaluate it at the end, that's enough to evaluate the initial H, but there's a subtlety for the superhorizon guys that we need to do this. So afterwards, my source is no longer active, but I do have expansion. And I can solve again, and then these coefficients are determined by matching at the end of the phase transition with the expression from the previous slide. So again, my initial power spectrum, I'm taking the 2-point function of these, the initial amplitude. And so this is what I've mentioned about the superhorizon modes. There's a bit of a subtlety with them. So I'm going to have to treat the two different regimes separately. And this is something that we didn't fully appreciate with the first iteration of this paper. So we have put out a new version. Just if you've seen the first version, look at the new version. Right. Okay. So the subhorizon regime here, there's no subtlety, and I can just define my initial amplitude as the perturbation that I solved for, evaluated at the end of the transition, which is this thing. Okay, and then I just plug this into my definition of the power spectrum, and then this is what I get for the dimensionless power spectrum. Where now this pi with the no IJ indices, this is the unequal time correlator of the transverse tenseless stress tensor at two different times. So that's kind of where all the physics is hiding. And we're going to hide it farther by defining this delta. So this is, the name of the game is really computing this delta. This delta is nice because here I've pulled out like the thermal phase transition parameters. So really this thing just depends on this ratio, of K on A star beta. And then computing this is a pain and is what, Gino and Takamoto did. And they did it kind of semi-analytically, which is really nice. I think I have a reference for that paper on the next slide. So if I define this as my delta, this is just what P of H becomes, and I don't know why that's offset, but, so right, this is the archive number for that paper where they actually calculate the 2-point function of the stress tensor for, the bubbles. And in the subhorizon limit, so when X is much larger than 1, this delta is just approximately 0.11 on X, a very good approximation. So my subhorizon spectrum at the end of the day just looks like this, where this kappa here, this is the efficiency factor for the energy density, or sorry, the energy going into the fluid. This is the transition strength, which is like the vacuum energy released in the transition over the background, like energy density and radiation. And then the other thing is I've introduced the conformal time at the time that it's taking place, just because this is more convenient than talking about A star and H. So I'll come back to this formula once I have the whole spectrum, but this is the rough schematic form.
Actually, maybe,
Yeah.
like, back to Keith and Gongjun's question, I guess their question is equivalent to what is this alpha? Is alpha usually very small? Like, how small is it?
Yeah, good. So alpha is typically quite small, and you might think that for a super cooled transition, which is like strongly supercooled, it might be generically large, but no, even when there is some correlation between the wall velocity and the strength of the transition, but it's not necessarily, like, I feel like in most particle physics
Right.
Oh,
The other one.
yeah, thanks. I think in most particle physics models I see like alpha being somewhere, say 10 to the minus 5 to 1 is kind of pushing it. You can have larger than 1, but I'd say something of like,
I mean, normally I would associate strongly first order transition with alpha much bigger than 1. Because that's what you mean by being super cooled. If it happens with alpha of order 1, it's happening with an energy density comparable to that of the radiation. And then if you want to super cool, then all of a sudden you become dominated by that energy density. I mean, it might be naive way of thinking about it, but that's.
yeah, maybe so. I do have like a little bit of a prejudice towards larger alpha, but because of constraints, we can't take that larger value of alpha.
That's fine, but then I don't know, why is it even super cool?
Well, it's super cool because the thing that characterizes the duration of the phase transition, this beta over H star, this has to be greater than 1. I think typically this thing is like somewhere of the order of 100 to larger, but the smaller it is, the longer the phase transition lasts. And we're gonna take it to be 2. Which is very long.
What physically is beta?
Oh, that's the inverse, sorry. Beta is the inverse duration of the phase transition. So this is comparing the time scale that it takes the phase transition to complete to a Hubble time.
That will, I guess, have more to do with the width of, and I assume there's a very, it would be helpful if there was if you had like a potential,
Yeah.
you know, or at least even a shape of a potential, which is, say, temperature dependent, so we can get an idea of where these scales are coming into.
Yeah, no, I completely agree.
Because these things are all related. If I write down some finite temperature potential.
Yeah, can you actually get these parameters that we're choosing?
Right.
No, I don't know. My hope is yes, but it's something that I'm looking at now. Yeah, that's what I mean by like actually getting these parameters in a realistic particle physics model. Like actually deriving them from the finite temperature effective potential.
Doesn't have to be a realistic model, even a toy model.
Okay, more than just like me saying I am God and here are the values. Yeah. Yeah, I'll think about that and I'll let you know.
at peak of this power spectrum that happens at the size comparable to the maximum bubble size, is that? Right?
Yeah. That will be in a few slides. Yeah. Yeah. And that's the thing separating the sub and super horizon regimes. Right. So the super horizon regime, this is a thing that we didn't really appreciate initially, is that when you excite a super horizon mode, it's kind of like, if you look at the equations, it's like exciting an overdamped oscillator. And the initial conditions are kind of that the amplitude is 0, but the derivative is non-vanishing. So it takes like a finite time actually for the mode to reach its maximum amplitude. And remember that we've decomposed H as this initial amplitude times the transfer function that's handling the time evolution. So we want to make sure that we're applying the transfer function only after the mode has reached its because the transfer function is just 1 when it's super horizon. So we need to wait sufficiently long that the mode has actually reached its maximum amplitude before we apply the transfer function. So because of that, we actually have to evaluate this at some time x of f plus epsilon, where epsilon is some less than 1 number. And in that case, you can show that this is the expression that you get for the initial thing, which you do the whole song and dance again, and then this is the expression that you get for the dimensionless power spectrum, which notably it looks just like the subhorizon case, except this delta is going to have a different limit, and also there's no k on a star h squared. So it's 2 powers of k different.
Say again, where the power on super horizon scales come from?
I mean, the reason that you get this k to the 3rd spectrum, which is like the white noise spectrum, is because the correlations are just random.
Yeah, but the amplitude is going to be tiny. Right?
Yeah, no, it's definitely suppressed. Yeah, it's suppressed. And the way that you can see this on the level of this equation is because it goes like k tau star cubed, and k tau star for these super horizon modes is much less than 1. The way you can see it intuitively is just because, again, exciting super horizon modes is they're damped. Yeah. So this is another reason why you would expect the phase transition not to give a contribution to B-mode polarization, just because where it matters for the CMB. So this is the super horizon spectrum is kind of like the IR tail. The spectrum looks schematically something like this. This is like a k to the cube. This is like a k to the -3. That's the peak. And then this is the super horizon region, or the IR tail. And then this is the sub horizon. This is curly P of H. I'll show better plots in a slide or so. But yeah, and then this is what the CMB cares about or whatnot. Maybe it's even like this. So yeah, there's not a lot of power there.
You say, when does the transition happen?
The benchmarks I'm eventually going to look at are like KEV and EV.
So the peak scales are like probably not that much smaller than the CMB scales.
For the EV one, yeah. Yeah. Yeah, the EV one is gonna, yeah, I'll get there.
Yeah. And again, associated with the fact that it's strongly first order, how much entropy produced? How much entropy is produced?
I don't have a quantitative answer to that, but we did look at the bounds from like ineffective and CMB anisotropies and spectral distortions, and also the scalar perturbations. Is that?
But I don't know. I mean, are you dumping in a factor of 1,000 entropy or a factor of 10 million entropy?
I mean, it depends on alpha. I mean, I should also give a huge disclaimer that we're imagining this happening in like a dark sector, not in the standard model itself. Yeah, this kind of has to happen in a dark sector, otherwise you are dumping way too much energy in way too late.
Because then it won't have the effect on this, then it will come.
Yeah, it has to.
to.
Yeah, exactly. I think that'll be clearer in a few slides when I actually show what this looks like for like two different points.
And if this happens in dark sector and then the energy radiation released from this region, this will not destroy light elements.
But it's dark sector.
Yeah. So if it's in dark, if it's in
Yeah.
dark sector.
Yeah.
So BBN does not like this.
Yeah, BBN does not, but you still do have like the general bound from like an effect if that's just gravitational or like, yeah. For dark radiation is still constrained. But BBN should be fine. Right, so this is the thing that you anticipated. The peak is kind of set by the maximum bubble size. If you do it a little bit more precisely, this is what you find. So in the subhorizon regime, we had that one expression, which I'll show in the next slide, in the superhorizon regime. In the far superhorizon regime, we know what this looks like, but admittedly, from the peak, when we compute the subhorizon regime, there's a few limits we have to take that make the calculation only applicable to like the far tail. So to kind of parameterize that uncertainty between the peak and the where the superhorizon scaling kicks in, there is some intermediate area that we don't know, and we would like to go back and calculate that a little bit more precisely. But in the meantime, we're just kind of parameterizing this with a power law. And now I'll show you what it actually looks like. So this is what the tensor power spectrum looks like. Here I have two kind of representative benchmarks. This has the solid green one is the 1 electron volt guy. So this one peaks just a little bit smaller scale than that CMB window function does. Here, this is what I'm calling the subhorizon regime, and then here's the superhorizon scaling. This part where it's like a slightly different slope. This is the area that we're not so sure about. This is like the kind of the regime where it's subhorizon but super bubble, or superhorizon but sub bubble. It's one of the two. I don't remember. But this is the regime where we would like to calculate it more precisely. It probably smooths out. It's probably not like a strict double power law. But and then this is the other representative benchmark. So this is 3 keV. So you see, as you increase the temperature, this thing is moving to smaller scales. And the thing is that this is roughly where that window function has support. This is kind of like the linear CMB sensitivity regime. So this is the part, and remember that the CLBB was this this integral. It looked like something like a d log k of curly p of h times the FL squared. So this is roughly where the FL squared is going to have support, which with, again, more support on larger scales. So this is where the contribution from the power spectrum is actually going to enter into the B-mode signal. So for the 1 EV benchmark, we're going to be sampling from the subhorizon regime, the peak, and a little bit of the superhorizon tail, versus the 3 keV, we're just going to get the tail. And we'll see this reflected in the shape of the B-mode signal in a slide or so. Yeah.
T star here is the temperature of the visible sector.
Yeah.
Right.
Yeah. It's a proxy for time.
And why does the transition have, if it's in the dark sector, why does it have any effect on the CMB at all?
Well, I mean, things like CMB spectral distortions, that's just sensitive to the overall power like, I mean, these are tensor perturbations, it's strictly gravitational.
They can still make
Gravitational tensor perturbations give temperature anisotropies like regardless of what sector they're in, just because gravity is democratic like that.
Okay, but usually, in the case of inflation, that requires a real lot of energy density because there's Planck suppressed, so you need to have H over M Planck, which is what's sourcing it, right? And here your scales are way, way, way down. So the amount of energy density that you're dealing with is also very small. So how do I interpret that having any observable effect on the CMB?
Intuitively.
I mean, you might be partly winning because, like, if the gravitational waves are produced during inflation and they redshift a lot by this time, whereas these are being produced like right before the combination, so it's less redshifting.
Yeah. Yeah, I guess maybe that's an argument for why this. Yeah. Yeah. I'll think about it, but that seems right. Okay, so now is the plots that I finally get to talk about. So this is the 1 EV benchmark. So here I have inflation in dotted blue, and then in the green is the phase transition. And you see that this is kind of analogous to the shape of the inflationary signal. It does peak at slightly larger L, so slightly smaller scale, which is consistent with the fact that oh, actually, I think I described why the shape is what it is in a few slides. Yeah, sorry. So again, this your amplitude is kind of the competition of these two factors. So this guy peaks around 0.1 inverse megaparsecs. In the inflationary case, this is just a flat spectrum, so it's really just going to follow the shape of this thing. So in that case, the dominant contribution is going to be around 0.01 inverse megaparsec, which you can show roughly corresponds to the peak being around a multiple of 100. And then it's got the wiggles and falls off on larger scales. Versus in the phase transition case, at least in the 1 EV case, because we're sampling from both the subhorizon regime, the peak, and the tail, we get it such that there's less power on larger scales there's less power on smaller scales because the subhorizon tail falls off. There's less power on larger scales because the superhorizon tail kind of falls off. And then the peak is just slightly displaced from the inflationary one. For the other benchmark where you're only sampling from the tail, this is kind of what you see. So this just generically peaks at much, much smaller scale. Yeah, it's a competition of where the phase transition power spectrum wants to have power versus where the CMB is sensitive to. And it turns out that, yeah, this is the shape you get. You can kind of see the thing transitioning between the two different shapes if you plot this sort of like color map. So here red is larger temperatures or earlier times, and the blue is later times. And you can see that as you start to get up here, this is where you start sampling from like the peak and the subhorizon regime instead of just the tail. Some of these are ruled out. This is just kind of showing the behavior, but so far as we can tell, these two are not. If you could actually, again, find a model that gives you these parameters self-consistently.
And the reason for the red one, you take a much higher alpha than for the green one, I'm presuming you can like get away with higher alphas if phase transitions happening earlier.
Yeah, yeah.
And maybe
Yeah.
I'll show that.
Yeah, the parameters we picked just to match the inflationary peak amplitude, and yeah, for this one, you can choose a higher alpha. Right, so that's the B-mode signal. Now, oh, I'm very low on time, but I just want to mention that there's kind of a complementary signature of this scenario, because these are stochastic gravitational waves. The same tensor perturbations give you kind of both signals, so you could expect that there's another observable that you could cross-check this with. To calculate that, we parameterize the energy density and gravitational waves via this spectral density parameter, which is the energy density and gravitational waves per logarithmic frequency interval divided by the total. Initially, at the time of the phase transition, this is how it's computed with this. This is the real space correlator, so it's an integral over the momentum space, pH prime. An important difference here is this is the dimensionless power spectrum of the derivative of the tensor perturbation with respect to conformal time. And with that one, there's no subtlety with the superhorizon modes. So the calculation actually goes forward just like in the subhorizon case. And this is what you get as your initial spectrum, which then, of course, you have to redshift to today. So this is the prediction that you have for the spectral density today, which you can also plot that for our two example benchmarks. Right, so the red one is the 3 keV and large alpha, and the green one is the 1 EV one and the small alpha. What else to say about this? Right. This is the inflationary CMB constraints. That's something that's model dependent. And then the other things in this plot are projected sensitivities for the square kilometer array and Lisa. And also the inflationary signal to compare with.
Just for curiosity, in between the first timing array constraint, first timing array and the B-mode search here, in between these two, we don't have any follow the stochastic gravitational effect.
Not that I'm aware of. If someone
Okay,
knows of anything.
No, just for curiosity, I want to know. There's
Yeah.
nothing there.
Not that I'm aware of.
Okay.
I mean, I don't know that there's too much motivation to look there. Sorry, what was that?
Right, this is the first time.
Here's
a timing array.
It's a rate that does. Oh, you mean like through the pulsars on the sky?
Yeah. This one.
Yeah, what is nanograv? It's like,
I thought it's similar to SK.
yeah, it should be like 10 to the minus 9.
I think it's similar to SK.
Yeah, I think the sensitivity just wasn't.
Oh.
Yeah, it's probably
Oh.
there. We just didn't plot it because this is projected to be more sensitive and that wasn't actually intersecting it, but we probably should have plotted it.
Because I have a signal, so I was just wondering if you were trying to fit that signal.
No. That would be nice, but yeah, because the nice thing with
You'll keep reading. It's like,
yeah, the peak frequencies here are too small, but that is the nice thing about this, because it does have two observables that, you know, if you see something that looks like this and you don't see the corresponding like or sorry, if you see a B-mode polarization signal, but you don't see the corresponding gravitational wave signal, then you know that that's inflationary or something else that I'm not aware of. Okay, sorry, I think I'm at time now, so I'll just end with some summary. So the tensor perturbations from a first order phase transition can produce B-mode polarization, and the signal strength can be pretty large if you have a late time transition, so like KeV or less, and your other phase transition parameters conspire to work out perfectly. The shape is distinct from the inflationary prediction, so if you can measure things on multiple scales, you can differentiate these things. You can also use the complementary gravitational wave signal to do a cross-check. And then, of course, these are things that I'm thinking about now. One of them is, can you actually get, starting from some toy model, starting from some finite temperature effective potential, can you actually get these sorts of phase transition parameters or not? And then also, there are other sources of tensor perturbations. We were just considering the bubble collision phase of a first order phase transition. I think honestly, you might have better luck if you look at the sound wave contribution. Also, interestingly, the k to the third scaling of the IR tail, that can actually be different in the sound wave case in a way that I don't understand well enough to explain right now, but would like to. And then also other sources of tensor perturbations, topological defects, what have you. And then also just putting limits on late time phase transitions, because I was kind of surprised that you can get away with a lot in a dark sector, even pretty late. Okay, that's it.
Particle physics model. What kind of physics are you thinking for this KV phase transition, UV phase transition in the dark sector? What's the physics behind the way you think?
Well, so if you want it to be, I'm still thinking about the physics at the level of equations, not actually like motivated model, except.
Yeah, I'm thinking more motivation.
Yeah, well, I mean, so if you want to look at the signal from like the bubble collision phase, then again, you want a potential that's classically conformal invariant. So like whatever model would give you that, but you shouldn't be constrained to that. That's just the only one that we've calculated the thing for. But I think more generically, thermal phase transitions are going to have the dominant contribution from the acoustic phase. So that should be, maybe we should do that next.
But I meant just like, why would you want a phase transition at EV energies in the dark sector? What could you do with that? I mean,
Oh,
what are you trying to solve? Is it for dark matter, or what are you trying to do? That's kind of like.
Yeah. I don't really have a motivation to be thinking about late time phase transitions beyond, hey, it gives you this cool signal that you can go out and look for.
Fine, but I was just wondering if people have thought about what they do with those kind of phase transitions, late time phase.
Yeah, I know that we did cite a paper that works on late time phase transitions that probably has the answers in there, but I haven't read it well enough to.
But there is some work.
People are thinking about it. Yeah.
So let me ask a brief question. Is this dark sector even in several contact with our sector at all?
No.
Yeah, so the temperature you're labeling
here is the same. That's why I asked before.
Yeah, it's
T star was the temperature of ours.
T star is the temperature of ours.
Yeah, so it's
because I'm just using it as a.
But it's so what temperature is it then in the dark sector?
That's model building. That's something I would have to find out.
You didn't care about the strengths.
Yeah. I just care about the time that this is taking place in our sector. But the dark sector could be at a much cooler temperature or much higher temperature.
Be a little careful about that, because if there's something thermal in that other sector, then it's going to contribute to the energy density. So I mean, once it's thermal, then it's out, then it's something to the fore.
Yeah, and
You
then
can't do that.
it bounds from ineffective and yeah.
Also, can I ask, is really your tensor perturbation, is it really solved by bubble collisions or just by in your calculation, bubble walls passing by each other and they remain their configurations? How do you, what, in your initial tensor perturbation, how do I interpret?
It really is the energy density, like,
So bubbles passing by each other, right? They have some
Yeah.
tensor.
yeah, it's more just,
There's no real collision happening.
yeah, again, the whole point of the collisions is just so you break spherical symmetry, but we don't really have to follow what the bubbles do after that. It's just, then you can use your expression for what T mu nu looks like for the scalar field. And calculate.
You want to have homogeneous.
Yeah,
They don't have naturally.
yeah, you don't actually need to follow the collisions.
It's just the bubble happening randomly, the extent that.
Yeah,
Give you enough perturbation.
exactly. We have a brief summary of that in our appendix, but this paper goes into a lot more gory detail with how that is computed. But yeah, it's what you just described.
This happens in dark sector. Can you give us just a number that you expect for delta effect?
Ooh, yeah. Okay, so this is kind of, I mean, these parameters were chosen kind of pushing up against the balancer.
Currently, I think we have sensitivity up to like order of pension -2, order of pension -2.
Mm-hmm.
And you mentioned CMB stage 4, so they will probe like pension -3. So I'm wondering.
Yeah, we're like,
what delta effect do you have in mind, which gives you this kind of, for example, strength of the stochastic.
Sounds very optimistic. L minus 2 sounds very optimistic.
Maybe that's one. Sorry, maybe.
Well,
you will probe.
isn't the present version like a 0.036 or something like that? Yeah. Okay, I think that's what we took. We took as much as we were allowed to do these benchmark points.
There's definitely correlation between the signal strength, for example, the strength of the stochastic gravitational wave background and delta effective. There must be correlation, I think.
Yeah.
Yeah, so therefore, as you showed your plot for stochastic gravitational wave background, I think there must be corresponding delta effective, which is supposed to be smaller than the current sensitivity.
Sorry, can you repeat that?
I guess there must be one-to-one correspondence between the height of this peak in this stochastic gravitational wave background plot and the delta effective, which is contributed by dark radiation released from this phase transition.
Yes, I would think so. Modulo, if you do something in the dark sector to dilute the energy more quickly, like this is kind of assuming some equation of state for your dark sector post, like to calculate ineffective, you're assuming some, I think there's a one-to-one correspondence if you're assuming radiation domination right afterwards. Yeah, I think there would be a one-to-one correspondence if you assume radiation domination
Yeah, I think
afterwards.
there must be correspondence.
Probably.
Therefore, this once you show this plot, this should be able to be converted to delta effective number. I think in your scenario, that should assume for the dark side. They will further constrain the scenario.
Maybe so.
Yeah. And also, as a comment, if this happens at such a late time, this will shift the peak location of CMB power spectrum, temperature and isotropic power spectrum. Yeah. So that's another thing that you can use to distinguish this scenario with others.
It'll shift the
It will
peak.
shift peak location. Because once you have a free streaming dark radiation, that will cause an isotropic.
Fair.
That will shift the peak location of CMB power spectrum.
Yeah. Okay.
Just
maybe kind of related to something Jonathan was asking, do you have like a parameter space of what alphas are allowed and like what the constraints are from ineffective or something like that?
I was really hoping to not show this slide. Yeah, okay. So these are our two benchmark points and this is what's allowed. The shape of all these constraints will change depending on what beta over H star is. And also depending on the equation of state in the dark sector afterwards. So in this plot, this orange region is the spectral distortion constraints from Kobe-Ferris. And delta N effective is actually pushed higher, like it's weaker than that, because we've assumed that our phase transition ends in conation. If you assume that it ends in radiation domination, they're kind of right up here flush with the Kobe-Ferris constraints.
What's the reason for this wiggle on the fire?
Right, so there's mu distortions and Y-type spectral distortions. And they kind of look like that, like this is the Y-type and this is the mu-type, and where they trade off in terms of which is the more constraining. There's actually a deep, this is the, so there are constraints on, I don't know, some power.
Yeah.
Some power spectrum.
Just interesting. That it's
Yeah,
the
but
same
there's,
one.
yeah, it's, actually, I think I have these backwards. Yeah, because this is smaller scales, yeah. But that wiggle is just where they trade off in terms of which is the more constraining. And I forget exactly. What it is.
More question. Well, at the early times there can be on the
Sorry, what?
at the early times there can be only a new discussion. The Planck spectrum.
Yeah.
With mechanical.
Yeah, yeah, the Y distortions are at later times once even, I think, constant scattering becomes inefficient, and then you can't even retain a thermal spectrum like that.
Okay, let's give a big applause again to the speaker. Very interesting topic.
Yeah.
Yeah, nice talk.
Thank you.
Sorry, I have to head out. I would like to join for lunch.
Oh, that's okay.
But still, it was an interesting talk.
Thank you. Nice seeing you. Ah, thank you.